Electrical machinery 1. Different losses and DC generator. DC generator topic. That is first column is mechanical input power from prime mover. Then it transfer to friction windage hysteresis and eddy current losses. That is rotational losses. Gross electrical power generator. Third, field current losses, shunt field copper losses, series field copper losses, brush contact loss, armature copper losses. Fourth step. Fifth step, losses on compensating winding, interpole winding loss. Sixth step, that is goes to net electricity power loss, that is output. Application, shunt generators. These are used for charging batteries because maintain the generator terminal voltage constant by adjusting the field current. Series generator, it is useful as booster to boost the voltage in the feeder, supplying power for distant loads such as electric fraction. Shunt generators, shunt field winding long feeder connections are shown in figure. That is, generator is parallel to motor and field rheostatic winding and shunt field winding. Series field winding is connected to series. The circuit diagram shown in figure. Applications of DC generators. Electrical machinery 1. That is compound generator. Cumulatively, compound generator is used to provide supply for large loads operating at a large distance from the sources. Example, electric fraction, overcompounded generator. In the case of differentially compound generator, the well-known application is the electric welding bearing. The load voltage must decrease as the load current increases. The load voltage must decrease as the load current increases. Compound generator or maintains almost constant terminal voltages over a large range of load. Hence, they are used where large load is suddenly there on edge of the generator and also for power supply purposes. Problem, DC generator OCC separately excited problem. The OCC of shunt generator is separately excited and is operating at 1000 RPM. The OCC as follows. OCC is 1000 RPM. Taper column is shown in figure, that is E and IF. If the generator is operated 1100 RPM as a shunt generator and the field circuit resistance is adjusted to 80 ohms, determine the following: no load EMF output power when the terminal voltage is 100 volt. The armature resistance is 0.1 ohm. The terminal voltage of the generator when the generator delivering having the maximum output current. Generator circuit shown in figure. Shunt generator. 1100 divided by 1000 is equal to 1.11. That factor is multiplied into 1000. We obtain OCC values. New OCC value is 1100 RPM. Previous tabulation E is multiplied by 1.1. We obtain OCC for 1100 RPM. E.g. new value is obtained. That is 56 into 1.1. The 112 into 1.1, 150 into 1.1, 180 into 1.1. Similarly, we obtain these values. RSH is equal to 80 ohm, V is equal to IR, V is equal to 80, 80 divided by 80 is equal to I. We obtain I value is equal to 1 ampere. Put IF and versus terminal voltage E graph 1 ampere and 80 volt. We obtain resultant value. Curve OCC is obtained from 1100 RPM tabulation. That is OCC curve at 1100 RPM. Field current report line, that is output power VL IL, that is output power. ISH is equal to VL divided by RSH. IL is equal to IA minus ISH. IA is equal to E minus VL divided by RA. DC generator electrical machinery 1. Obtaining internal and external total characteristics from OCC. The curve is shown in figure. IFS E0. Circuit shown in figure. Long shunt generator circuit. Load is connected. Series field winding connected. Rheostatic varied resistance is connected. Shunt field winding is connected. VL is load voltage. Figure C, we obtain graph drawn different armature current. External characteristics and internal characteristics we obtain. Current versus voltage. Red line's curve is external characteristics. Green line is internal characteristics. DC generator tabulations we obtain from internal and external characteristics test. Procedure, assume VL. VL RSH is equal to IF. From IF get E0 value. From E0 get IA value. IA is equal to E0 minus VL divided by RA plus RSC. IL is equal to IA minus ISH. Given values RA, RSC, RSH. Internal graph we obtain EG versus IA. External graph we obtain VL versus IL. OCC of a generator run at a fixed speed. Critical speed NC is critical speed of a shunt generator is the speed for which the given shunt field resistance represents critical resistance. NC is BC divided by AC into full speed N, where NC is critical speed. That is BC divided by AC is obtained from graph. Next page we will see graph. That is curve 1 and curve 2. RSH is tangent to the curve 2. A is tangent to the curve 1. From this value we obtain AC and BC values. The machine will fail to excite, that is there will be no build-up of the voltage. If the resistance line just lies along the slope, then that value of field resistance the machine will just excite. The value of resistance represented by the tangent to the curve is known as critical resistance OC for a given speed. The generator total characteristics. First point, if load resistance is decreased, then armature current increases up to a certain load current values. Second point, after that any decrease in load resistance is not accompanied by increase in load current. Third point, rather it is decreased and the EI curve turns back as shown in figure C. If the load resistance is too small, then the generator is short circuited and there is no generated EMF due to heavy demagnetization of main poles. Fifth point, line draw tangential to the internal characteristics curve and slope goes the value of the minimum resistance with which the generator will excite if excited on load. Graph drawn terminal voltage with different armature currents we found a total characteristics curve.